So I want to start by giving, oh, good.
I'm sorry.
Oh, it's okay. So I want to start by giving kind of a high level overview of some of the things that we do in my lab. And we're going to start out kind of big picture, just what are the big problems we work on. And then we're going to talk a bit more about how machine learning can help, and also give some examples in my favorite field of fluid dynamics. So this is kind of a rough diagram of how I organize the world into topics. So pretty much everything I care about lives in this blue box of dynamical systems, things that change in time. So fluid flows, over a wing or inside of a jet engine are dynamical systems that evolve in time. Your brain is a highly structured, complex set of neurons that are constantly evolving and changing in time, their dynamic state. Epidemiology, the spread of a disease across a continent, is a complex dynamical system. So pretty much everything I care about is in this blue box. And we don't just want to model and predict and understand these systems, but we also, in many cases, want to be able to control them, to suppress the disease spreading across a continent, or to halt a seizure that's propagating across a brain, things like that. And so a large portion of my lab works on building these dynamical systems models, which are typically of the form of a differential equation, some rate of change of some variables as a function of other variables. And we do this using kind of these emerging techniques in machine learning. So we want to learn physical dynamical systems models from data using machine learning. And we put a real premium on models that are interpretable and that are generalizable. So I'll get back to this a little bit later, what I mean by that. As I mentioned, we don't just want to model the system dynamically and get a differential equation. Often we also want to control the system and modify its behavior for some engineering objective. So again, in my field of fluid dynamics, we do a lot of work with my collaborator, Brian Pelagi, and others on trying to use these machine learning techniques to control our fluid systems, to manipulate the fluid flow, to extract as much power as possible, for example, in these cross-flow turbines. This is an industrial scale turbine that is being placed in a river in Alaska, so a very remote river, where this is the only power source for the village. And so if you can bump the power by 50%, that's a pretty significant engineering goal for that community. And we do it by, again, applying these machine learning optimization techniques to extract as much power as possible. And then the third big aspect of what my lab works on is in using these kind of optimization and machine learning techniques to figure out where would you place sensors and actuators in a high dimensional complex system. So for example, if you have, if you have a disease spreading on a continent, where are you going to put surveillance centers to capture the information as accurately as possible to infer the things that you're not able to measure? Similarly, with a Boeing or an Airbus wing, there's very, very complex fluid dynamics evolving on this wing. If you had 5 pressure measurements that you could take on a wing, where would you place them to have the best inference of all of the places you're not able to measure? So these are really, really significant engineering problems. And actually, this one is very much inspired by biology. So this is work I do with my wife, Brunton, who's also a professor of neuroscience at University of Washington, where we look at the sensor and actuator placement on insect wings. So it's very, very fascinating. These insects are able to interact with very complex, turbulent fluid environments. They're able to fly in very, very complex flow environments. And they are currently, their performance is way above our engineering systems at similar scales. They're very agile, they're very efficient, very flexible flyers. And it turns out, this is a really fun fact I didn't know about until recently, all flying insects, every single one of them, have on the order of 100 strain-sensitive neurons distributed across their wings. So those are the little red dots here that you see. And these are literally neurons that fire when the wing undergoes a certain bending pattern in time. And so there have been laboratory experiments at the University of Washington and elsewhere that have shown that if you take this insect, this is a moth that's about the size of my hand, and you hit it with a gust of wind, it can react, it can compensate for that gust and start to correct its flight behavior faster than that information can go from its strain sensors up to its brain and back to its muscles. So it's faster, it has a faster reflex than it actually takes to think about the measurements. And what that suggests is that there are local computations happening directly in the shoulder muscle. So these sensors are going up to the shoulder muscle. There is a local computation, like kind of a local brain making decisions about how to directly take that sensor information and use it for fast, flexible control. So this is kind of amazing. This is what we call proof by existence of this enhanced capability of having distributed sensors and local computations to make very good control decisions in very complex environments. And so a lot of our work is fundamentally inspired by this property. And you'll notice that these red sensors, they're not everywhere. They are somehow sparse, and they are placed in strategic locations to get as much information as possible, the most useful information that informs this insect's daily life. Okay. And this is kind of a fun evolution. So we started studying this moth sensory system about 10 years ago. Tom Daniel, who's pictured in the middle, has been studying this for decades, for a lot longer, but Bing and I started studying this 10 years ago. And what we learned was essentially a mathematical optimization strategy for how, if we were engineers and we had a fixed number of red sensors, where would we place them on a wing to make the best estimate of the flow state or the control state possible? And this is the thing I absolutely love about math and engineering modeling, is that something we learned because we were curious about how insects fly, that same mathematical architecture was valid when we worked with Boeing almost 10 years later to help them assemble their aircraft more efficiently. So this is a fun story I'll tell you about because it's just interesting, and it's a Pacific Northwest success story. So this is a picture taken from the Boeing factory. And apparently, again, another fact I didn't know about engineering systems until I started working with Boeing, is that every major aircraft, every aircraft you've ever been on, is held together with on the order of 1,000 custom-made shims. So shims, like when your table wobbles, you put a little piece of wood under it so it stops wobbling. That's the kind of shim I'm talking about. So even though these aircraft are made to exacting very, very high tolerance specifications, when you build these pieces up from thousands of constituent components, small imperfections start to accumulate, and they can eventually add, a centimeter of gap in certain locations, up to a centimeter. It's a pretty large gap. So when you're joining the wing to the side of the body of this aircraft, which I've highlighted here, the places that should fit perfectly together, sometimes there's little bits of gaps that you have to shim together. So in the olden days, back in the 70s, when you would build an aircraft, you would literally have to dry fit everything together. You'd put everything together. You get your smallest team member to crawl inside the wing and measure all of the gaps by hand and write them down on a piece of paper. They would disassemble the entire aircraft. They'd make the shims, they'd put the shims in place, and they'd reassemble it a second time. So building an aircraft was essentially twice as expensive as it should have been for a long time. In the modern era, we do that dry fitting digitally in a computer. So they have these very expensive machines that take point cloud measurements, kind of like your Xbox Kinect, really expensive versions of the Kinect that measure the spatial locations of all of these parts, and they digitally dry fit them to see where the gaps are going to be so that they can then digitally shim this aircraft. But that still takes a huge amount of time, something like 24 hours of time is, yeah, I'm making that number up, but it's a lot of time in the production of an aircraft, something on the order of 8 to 24 hours that is having to measure all of these points and then to digitally dry fit this aircraft together. And so what we did essentially was we used this moth technology, right? Like this is millennia, millions of years old moth technology of optimizing where you would measure a system as effectively as possible to infer as much as possible. And we moved that over to this Boeing shimming problem. So instead of measuring terabytes of point cloud data all across the wing and at every single piece, we could target based on patterns in the data, where would you measure if you were going to measure 1% of those points to get as much information about what the shims required are going to look like. And so we dramatically reduced the amount of measurement time and computation time required to shim this aircraft. And there are, like, this is actually in production on the 777X, the 787, the 737 right now today at Boeing. which is kind of cool. It's almost never do math algorithms that come from, completely curiosity-driven research actually end up in production in a major company. And they project that the savings in those programs over the lifetime is in the many hundreds of millions of dollars, which is super cool. So just goes to show you that math really is universal and that you can kind of use these very flexibly. Okay, good. So that was the basic picture, is that we have this kind of big picture diagram. There are complex systems that we want to model, predict, and control in blue, and we can use machine learning to build models of the system in blue, or to build the controllers directly, or to optimize sensors for how you would measure the system in the field. And so now I'm going to start going into some other examples of how we do this for the field of fluid mechanics, which is my field. So fluids are amazing. They're everywhere. We literally live and breathe and work inside of a working fluid. And so do all of our machines pretty much. And so I think this is a really exciting problem, because if you can improve our ability to model or control a fluid flow by even a few percentage points, this has huge economic and environmental impacts in less fuel burned, more efficient vehicles, less carbon dioxide, just in general, kind of every aspect of our economy and society can be improved pretty significantly by relatively small marginal increases to our ability to model and control fluids. And I would also point out that a lot of the science fiction future that we envision is kind of under the hood, partially going to be enabled by advanced flow control. Okay, so this is one of the systems I care about. And so I'm going to talk about why machine learning can help us solve some of the really hard, really old problems in fluid mechanics. And I'm going to just give a very, very simple definition of machine learning. So I know a lot of you in the audience probably know as much or more about it than I do at this point. But I'm just going to, very oversimplify my definition of machine learning to be, it is the process of building models from data using optimization and regression. Okay, so we've been building models for at least 2 millennia, right? 10 millennia if you count trying to build models of the solar system, classic astrology, modern astronomy. We've been building mathematical, physical models for at least 2,000 years, since Aristotle and before. Now we're building models, particularly, data-centric models, and we're using advanced optimization and advanced regression algorithms, and we call that machine learning. So in the field of fluid mechanics, there are a number of tasks or challenges that we have that optimization, that these machine learning optimization can help with. So the tasks in blue that I think about on a regular basis is how to reduce the dimension of a system. So my fluid flow, if I want to simulate it on a computer, these are typically supercomputer computations. If I want to simulate a wing or simulate an engine, I need a very, very expensive supercomputer with thousands or millions of cores that are running in parallel to simulate all of the scales of this fluid flow. And so finding a way of reducing that dimensionality from millions or billions of degrees of freedom down to a handful of key features that matter for my engineering objectives. Again, think about what the moth does. It's flying around in a very complex flow field, again, millions or billions of degrees of freedom to model or to simulate, but it doesn't care about every single degree of freedom. There are kind of patterns that it cares about for its daily life of flying and turning and generating lift. Other things I care about in fluids is, again, sparse sensing. If I'm going to put a few point measurements in an engine or on a wing, where do I place them? How do I use those to estimate the flow state and eventually to control the system to increase lift, decrease drag, enhance mixing, things like that. All of these tasks in blue are optimization problems. They're very hard optimization problems because the flow physics are nonlinear and multi-scale. And the pictures you see on the left kind of give a feeling for this multi-scale nature. So literally, if you have a complex fluid flow, there will be vortices of many, many, many size scales. There will be big vortices and medium and small and smaller and tinier, all the way down. Sometimes there are 10 orders of magnitude of scale separation between the biggest and the smallest vortices, for example, on a modern submarine or aircraft. And so the nonlinearity and the multi-scale nature of the physics means that when we try to solve these optimization problems in blue, they end up being very high dimensional, very non-convex optimization problems. And those have been challenging us for at least 5 decades in the computational era when we've actually been trying to solve these on computers. But these are exactly the kind of problems that machine learning is getting really good at handling. So if you think about training a really big deep neural network, that's also a high dimensional non-convex optimization problem. So we're starting to get a lot better techniques for solving these optimization problems in pink that are going to enable us to start solving these fluid dynamics tasks in blue. And I want to point out, again, I'm talking about fluid dynamics because I love fluids. They're super interesting. And there's a lot of really important applications of fluids. But almost any dynamical system that you care about has a lot of these same challenges and a lot of the same properties of their optimization problems. So if you are interested in neuroscience, right? My wife is a neuroscientist. Her system is also high dimensional and nonlinear and multi-scale. You have 100 billion neurons in your brain. It's very multi-scale in how it's organized in space and in time. It's very nonlinear. And you have the same tasks in blue. We want to sparsely sense, estimate, and sometimes control the system for like medical applications. Disease modeling, epidemiology, has the exact same hallmark features. It's high dimensional and it's nonlinear. So if you think about, every single person on Earth as an agent interacting and spreading diseases through their, going to the store and getting on a train or a bus, that's a very high dimensional nonlinear dynamical system. Again, we want to sparsely sense and estimate and control this system. So I just want you to know that every example I'm talking about in fluids have these strong parallels to other complex systems that we care about in neuroscience and epidemiology, the financial markets, you name it, there's applications there. And the reason that we think that we can solve these problems in blue in fluids and using machine learning is because there are patterns that exist in your data. If there weren't patterns that exist in your data, you would have a really hard time justifying these tasks for fluids. And also we wouldn't necessarily hope or think that machine learning is going to help us. So this is kind of an interesting, there's a whole rich history here. Fluid dynamics, modern data-driven fluid dynamics and modern machine learning actually grew up together over the last 75 years, starting with Kolmogorov. There's a lot of parallels of the development of machine learning and fluid dynamics together. And they both fundamentally rely on the fact that patterns exist in your data. Even in very high dimensional data, very, very complex systems, there are often these low dimensional patterns of activity that emerge. If you want to read more about this, we have this kind of cool review paper led by Sam Tyra from the University of California, Los Angeles, UCLA, where we talk about how to extract these patterns and use them for these objectives. Okay. But the existence of patterns is really the fundamental starting place if you're going to use machine learning to solve these tasks. So now what I'm going to do is I'm going to go into a few little vignettes of how we use these patterns to do kind of really neat things in fluid dynamics using pretty simple machine learning techniques. And again, when I think of machine learning, in my mind, I'm always translating machine learning is building models from data with optimization, exploiting the patterns in your data with optimization. Okay. So the first example is some really cool work by Isabel Scherl, who is a PhD student in my lab and co-advised by myself and Brian Polaggi. And she's actually just about to graduate in a month, so we're super excited. And this is really, really great work that she has done. So Isabel is an experimental fluid dynamicist. She runs laboratory experiments and measures the flow fields using a variety of techniques, but primarily laser sheet measurements. So you illuminate the flow with a laser sheet, you drop particles in the flow that are neutrally buoyant, and you can see the motion of those particles and infer what the flow field looks like. Now, anybody who measures flow fields experimentally knows that the fluid flows you get often look like a nice, clean fluid with television static on top of it, with noise and kind of outliers on top of it. I realize that many of you might be too young to know what TV static is. Now, in the olden days, when you turned your TV on to a channel you didn't have, it looked like white noise. I think now it just goes to a blue screen. But what I mean is that there is this flow field with these kind of salt and pepper corruption that are just kind of scattered throughout the flow field. And of course, Isabel is an excellent experimentalist, so her flow fields never look this bad. This is kind of a cartoon of how bad things can get. And so what we designed was essentially a machine learning optimization. So you can see with your eyes, there are patterns in this data, even with all of that crud on top of it, you can see the patterns. And so what Isabel designed is a machine learning algorithm, an optimization algorithm that can split this data set into a clean version, this low rank component L, and a separate movie that has all of the sparse outliers. And this is not a dramatization. This is the actual output of her algorithm on this noisy data set X. You can even see the little pox here to kind of show that we're not cheating. This is actually the output of the algorithm. Okay, good. And so again, this is relying on the fact that there are patterns in the data, and we're building a model of those patterns and using optimization to split the data matrix X into two matrices L plus S. Now you should be saying to yourself, this is way too good to be true. There are infinitely many ways of taking one movie and writing it as the sum of two movies L plus S, or taking one matrix X and writing it as the sum of two matrices L plus S. This is ill-posed. There's infinitely many solutions. How am I going to find this particular solution that I want? And so again, this, sorry, I'm like, need to get rid of my cursor. So the magic of all of this and machine learning in general is in writing down the right optimization problem, writing down the right objective or loss function or objective function that captures the essential solution, the features of the solution that you want to find. And so out of all of the possible L's and S's that add up to X, we want the L that has the minimum rank, the fewest linearly dependent columns. And we want the S that is as sparse as possible, that has as many zero elements, the smallest zero norm possible. Mathematically, that's given by the rank and the zero norm. It turns out that this is a non-convex optimization problem, meaning that it will not scale with Moore's law, and you can't apply it to big problems like this fluid flow. And so instead, what we do is we relax that non-convex optimization problem into this convex relaxation. So instead of the rank of L, we use the nuclear norm, which is the sum of the singular values. And instead of the zero norm, literally counting the non-zero entries of S, we use the one norm, the sum of the absolute values of all of the entries. And this is a convex optimization, and this does scale with Moore's law to much, much larger problems, to huge turbulent data sets. And so this is the optimization we run, the particular data-driven optimization to find this particular splitting L and S, where L has all of the patterns and S has all of the outliers and noise and occlusion. So I think this is kind of a cool, simple example of how you can apply these methods in kind of scientific and engineering applications. And I'll point out, this is kind of a lesson we can learn, is that if we as scientists and engineers have data sets that look like videos or images or audio signals, if we can interpret our data as a moving sequence of images, a movie, or as an audio sequence, immediately you can leverage billions of dollars of machine learning technology that's been built for images and for audio signals and for speech translation and for movies and compression, by companies like Google and Amazon and Facebook and Microsoft. So immediately you get all of these great off-the-shelf tools essentially for free if you can interpret your data as a video or an audio sequence. Okay, so once we have decomposed this noisy data set X into a nice clean data set L, you can do things like find its modal decompositions, and you get much, much cleaner modes in the right column. This is after cleaning this RPCA than in the middle column, which is when you apply this to the noisy data, and you get better models too. Okay, so that's one example. So the second vignette is kind of related, which shows us, again, if I can think of my flow field as an image sequence with patterns in the data, I can do other things like super resolution. So super resolution is a really cool technique. People have been developing this for decades, but it's gotten really good in the last 10 years. And again, the idea is I can take a low resolution image like the one on the left, and I can infer what the corresponding high resolution image would be that generated that low resolution data. Again, you should always be asking yourself, you should be skeptical when people talk about machine learning and what they can do with it, because this seems too good to be true, right? Like there are infinitely many high resolution images that could generate that low resolution image on the left. But again, this always gets back to the point that there are patterns in the data. There are strong patterns in human faces. If I take my glasses off and I look at both of these images, they actually look pretty similar to me. And I know that I'm looking at a human eye, and I know that eyebrows are composed of hairs, and there are eyelashes and irises. And I can infer with my mind's eye, with my imagination, something about what would be underneath these pixels, based on the structure, the patterns, the statistical correlation of what we know goes into a human eye. Okay, and so that's why super resolution is possible. It's not perfect, but in some cases it's possible. And so you can apply this to engineering systems like fluid flows. And again, this is a major technology enabler, because often we are limited by our measurement technology. We can't measure all of the scales of the flow, even though the flow looks like the picture on the left, snapshot A. Often what we can measure with our cameras looks like the middle column, snapshot B. And so we would like to use the statistics, the patterns of that fluid to infer kind of a high resolution fill in of all of that data. And so in this work by Ben Erickson, who was a postdoc working with Nathan Kutz and me, we use a shallow decoder neural network to take the low resolution image in B and infer a high resolution image C that is in as close agreement to the true flow field in A as possible. And so of course we need a bunch of training data of high resolution and low resolution snapshot pairs. And based on that training data, we can learn the statistical patterns to infer from low resolution data what the high resolution image was. And so it actually works really well. So if our training data are these dark gray columns, and our testing data are these light blue columns, you actually get very good fluid flow reconstructions that almost perfectly match the actual test data in these light blue columns. But this is what we call an interpolation problem. And I think this is another point that's really important for all of you in the audience to know, is that machine learning, and deep learning in particular, are very good at interpolation tasks. It's good at interpolating between two things you've seen before. And essentially that's what we're doing here, because all of these blue columns, all of these test data are kind of sandwiched between things we've seen before, examples in the training data that are close by. Okay, this is why image networks is because an image classification on Google is because any image you can present is close to an image that was in their training data set. Okay, they have 1,000 examples of a truck and 1,000 examples of a coffee cup. And so anything you can present, there are examples that it's seen before that are kind of like that. But for physics, if we're going to use these fluids in the field to predict, we're not going to be sandwiched between training data. So we need to have our machine learning task work a lot more like this, where we train on the first 70% of the data in time, and then our model is tested on the next 30% as it rolls out into the future. And you'll notice here that the snapshot, the first light blue column, actually looks pretty good. It has fairly good agreement, but very rapidly our prediction starts to degrade and look really terrible. And so this is a cautionary tale that machine learning techniques are typically very bad at extrapolating. They're bad at projecting into the future into data that's unseen before, okay? And a lot of people are talking about using machine learning models to predict the climate and to predict how the geophysical fluid dynamics around planet Earth are going to be evolving in the decades to come. And this is both, I think, an exciting opportunity because there's a ton of data, but it's also, I want us to be very cautious because I don't think we believe that the next 30 years are going to look like the last 70 years. And so our training data is fundamentally not representative of the future data. And so this is really an important cautionary tale of just blindly applying neural networks trained on training data to roll them out into extrapolation tasks in the future. And so I would argue that the only way that we can hope to actually have models that will work into the future, into this extrapolation regime that we haven't seen before, is by incorporating some elements of the underlying physics of the system. Okay, so we can't just apply machine learning and forget everything about our physics that we've learned over the last 2,000 years. Machine learning does not replace physics. And currently there are efforts to start to bring these together so that you can incorporate partially known physics like symmetries and conservation laws and things like that into these enhanced machine learning models so that you can build models from data that have some hope of generalizing into the future. Okay. And so that's the last piece I'm going to talk about, is kind of my view of how we need to incorporate physics into these models and how we might go about doing so. So this is, again, I'll give probably 2 or 3 minutes of my philosophy, and then I'll give you some examples of how we're doing it. So we really need machine learning models that are interpretable, that humans can understand and interpret and explain and communicate, and that are generalizable, that can be trained based on some subset of the data and that work for completely unseen scenarios. Okay. Now, I'm not going to define what I mean by these terms, interpretable, generalizable. I'm just going to give you an example of like the ultimate interpretable generalizable model, which I would say is Newton's F equals ma, Newton's second law. So it's clearly interpretable in the sense that it has 3 terms, F, M, and A. They have units. You can write these down for a particular problem of interest, and you can go to a coffee shop and talk about them with a friend and discuss and communicate what they mean. It's very interpretable. And it's generalizable in the sense that you can learn F equals ma from an apple falling on Earth. At least that's how the story goes. And this model is still true when we land humans on the moon. That's an incredible leap of generalization that we would love for our machine learning models to have, but they certainly don't at this point. Now, you could build a neural network on videos of apples falling. You might need 1,000 videos of 1,000 apples falling. And this neural network will learn to generate new videos of new apples falling that will fool all of us in the audience. Like, none of us would be able to tell truth from fiction. But that machine learning model is not going to be useful when we decide to land humans on Mars. So that kind of points out the absurdity of how limited the generalization capabilities are when we want to use them for physics tasks. So we want models more like F equals ma. And it's not just F equals ma and Newton. This has been a principle in physics modeling from Aristotle to Einstein for 2,000 years. There has been this principle of parsimony, that the bits of a model that generalize, the bits that we would call the physics of the system, the way we find them is by finding the model that is as simple as possible, but no simpler. That's like the statement of what it means to be physical, of what it means to generalize, is you try to model your phenomena with the simplest model that describes your data, but no simpler. And so in the mathematical era, fast forward now, and we have 2 mathematical techniques in machine learning that we can use to promote those kinds of models that are as simple as possible, but no simpler. We want our models to be low dimensional. So in my fluid flow that has 1,000,000 degrees of freedom, I want to find a few key variables that describe the key features of that flow that really matter to me, maybe 3 variables instead of 1,000,000. And I want my models to be sparse. I want a differential equation for how those variables evolve that have as few terms in the right-hand side as possible. So those are our mathematical tools for obtaining these kinds of models that have a hope of generalizing and are interpretable. And again, in a machine learning context, that looks a lot like a deep autoencoder network, where you take a high dimensional data set X and you try to find some low dimensional features Z that capture as much of the variance or information of that data set as possible. So that's low dimensional Z. And then I want Z to be modeled as a differential equation, ddt of Z equals some function of Z, where that function has as few terms as possible. It's as sparse as possible. Those models have the best hope of being interpretable and generalizable. Okay, so in the computational era, in the modern era that we live in today, where we can run supercomputer simulations of fluid dynamics like this one, the kinds of models we want look a lot like the Lorentz 1963 model. So Lorentz, in his famous 1963 paper, where he wrote down this butterfly attractor for chaos, he was trying to describe chaotic thermal convection in the Earth's atmosphere. Looks a lot like this movie I'm showing. And he did it by extracting 3 spatial modes, the amplitudes of which are X, Y, and Z. I'm going to pause my video because I'm getting latency issues. That are modeled by X, Y, and Z. Those are the amplitudes. So it's low dimensional state, X, Y, and Z. And the differential equation on the right-hand side you see there is sparse. out of all of the possible differential equations that could describe the coevolution of these variables, there are 7 terms on the right-hand side and 5 of them are linear. It's about the simplest differential equation that could describe this data, but no simpler. So it has those properties we're looking for. So what we're going to do now is use machine learning to automate this procedure. So given data like this, can we learn these low dimensional sparse dynamical systems purely from measurement data, purely using machine learning? So this is an algorithm we developed just over 5 years ago called the Sparse Identification of Nonlinear Dynamics, the SINDY algorithm for short. And I'm going to show you how this works on the Lorentz system. So we're going to have measurement data of the variables x, y, and z, and we're going to try to learn what was the differential equation that generated this data. So the simplest thing we could do is try to build a linear least squares model, a little 3x3 A matrix that best fits the derivatives x dot, y dot, z dot in terms of the data x, y, and z. This is going to be a terrible model because a little linear system can't capture the chaos and rich behavior of Lorentz. So what the SINDY algorithm does is it augments the right-hand side with nonlinear terms that could describe the dynamics. Instead of just x, y, and z, now I have things like x squared, xy, y squared. In this case, polynomials up to z to the 5th. And now the goal is to find the sparsest, the fewest combinations of this library theta that add up to equal x dot, that add up to equal y dot, and that add up to equal z dot. And this sparse regression or sparse optimization is a set of optimization algorithms for machine learning that have developed a ton over the last 20 years. And now there are dozens of commodity algorithms to find these sparsest combinations of theta equal x dot, y dot, z dot. And you'll notice that the terms that are highlighted here, these models are as simple as they can be. If you dropped any term, red, green, or blue, the model would break. So these models are as simple as they can be to describe the data, but no simpler. So they have that principle of parsimony. And you'll see that the terms that are highlighted in this sparse regression model, purely from the data, are exactly the terms that were in the differential equation that generated the data. So this is pretty cool. You can actually learn the nonlinear dynamics that generated your data purely from the measurement data. I'll point out we have open source code in Python. So if you want to play around with this and try it out yourself, we pretty much have open source code for all of our stuff that we develop. So you can try this out called PySindy. You can also use this to discover partial differential equations. So if I have data from a fluid flow like this is work by Sam Rudy when he was a PhD student with us. If I have data from a fluid flow like this, you can again build a library of partial derivatives and products of partial derivatives. And with sparse regression, you can learn these partial differential equations like the Navier-Stokes equations. So there are some options here. I'm going to summarize how you can build these sparse interpretable models from data. So the goal is to take data and build dynamical systems models that have this interpretability. We want differential equations like x dot equals f of x, or partial differential equations like partial u of t equals some function of partials of u with other variables. If I have my Lorentz data, then this algorithm will give me things like a sparse ordinary differential equation like Lorentz. If I have a fluid flow, a spatial temporal system like this, I will get a partial differential equation like the Navier-Stokes. The third option, actually, this is more like what Lorentz did, is that if I have that fluid flow, I can possibly break it up into a modal basis, into a low dimensional basis of orthogonal modes, where that flow is approximately x times that first mode plus y times that second mode plus z times that third mode. And then I can build a differential equation in terms of the amplitudes of x, y, and z, how they evolve in time. Okay, and so all of these are possible with this SINDY algorithm. So I'm not going to kind of go too far into the examples of this. I'll just throw this picture up to show that we have applied this to a ton of complex systems. In the lower left, we have a fusion reactor, three-dimensional fusion reactor we've modeled. Right next to it, we have this turbulent wake experiment from my collaborator, Richard Zeman in Germany, and kind of all of these flow fields. You can build these simple low-dimensional differential equations, x dot equals f of x, where x is a low-dimensional state that captures the key features of the fluid flow, And F is a differential equation that is as sparse as possible. It has as few terms as possible, but no fewer. And in all of these cases, we get better interpretability and better generalization capabilities because we're adhering to this age-old physical axiom of getting the simplest model possible, but no simpler. Okay, so I just think I want that to percolate that, machine learning, people often think of these huge neural networks that are, as deep as possible with as many parameters as possible. And those are powerful and they're useful. But sometimes we like simplicity and sparsity because those help us to generalize. Okay, maybe the last thing I'll point out before I go to questions is, remember this picture I showed here. For all of the examples I showed you, we basically already started in this low dimensional latent space Z. So Lorentz, in the Lorentz model, I just picked, those three variables, X, Y, and Z, those were already low dimensional. He had already found the transformation from the high dimensional fluid flow down to that low dimensional space. But what about when we don't have those coordinates? If I want to model the brain, I don't know what the right low dimensional coordinates are. So I have to learn those low dimensional variables. And there's another interesting parallel to the history of science here, which is from astronomy. So this cartoon illustrates what humans have seen when we look up at the night sky for 10,000 years. So we're the blue dot in the middle, and when we look up at the sky, these are the motions of the sun and the planets. And notice that they do crazy things. They sometimes change direction mid-course. This is why we name our gods after the planets and our planets after the gods in many kind of mythologies, is because these planets appear to have agency in this coordinate system. They're very unpredictable. And sometimes you need to pick the right coordinate system where you move the Earth out of the center and you put the sun in the center. And now the motion of everything is much more simple and predictable. And so Newton wouldn't have been able to learn F equals ma if we hadn't started with a good coordinate system from Copernicus. Okay, and so that's really what this picture is trying to show here, is that to learn these sparse dynamics z dot equals f of z, often we need to find the right coordinate system into that coordinate system z. And so this is work by Kathleen Champion, she was a PhD student working with Nathan Kutz and myself a few years ago. Really fantastic work. This is some of the coolest work that came out of the lab in the last 10 years, where she coupled a deep neural network to learn that coordinate transformation with a sparse interpretable SIMD model in that latent space Z. So kind of building on the power of neural networks to find coordinates, and on the simplicity of SIMD models to explain how those coordinates evolve in time. So I'm not going to give you too many examples of this, but just to show that you can combine these architectures to simultaneously learn good coordinates and learn the dynamics. So kind of like learning, to put the sun in the center of the solar system and learning F equals ma kind of simultaneously. Okay, so I think that is a great place for me to stop. I'm just going to summarize. Machine learning is optimization with data. If you want to apply this to physical systems, we hope that it's interpretable and generalizable. And the way that we can build in interpretability and generalizability is to capture the essential physics of your system, where my definition of physics is getting the model that's as simple as possible, but no simpler. So promoting sparsity and low dimensionality are really powerful tools at your disposal here for building these interpretable models. Okay, so I hope we have a little bit of time for questions, and thank you all for your attention. I appreciate it.
That was just honestly amazing. I learned so much, and just thank you for the presentation. And I was just curious on like how you began to what caused you to start your journey in artificial intelligence?
Yeah, I mean, I've always loved math, and I've always straddled kind of math and engineering. So my first degree from Caltech was in pure math, and then my next degree was in aerospace engineering, and then my next one was in applied math. So I've always been kind of back and forth. Mm-hmm. And even before we talked about machine learning and artificial intelligence, a lot of the work we did was data driven. So we had very high dimensional data sets, like in fluid flows, right? We always have these huge simulations, very, very expensive, generate terabytes of data. So we always had big data. And we have always been developing techniques to extract patterns from that data to simplify it, to simplify our downstream tasks. And so it kind of was very natural. Like when I started as a professor at University of Washington, there was this very natural transition that a lot of the techniques we had been developing already in fluid mechanics kind of naturally fit into these data-driven optimizations. And machine learning had gotten so powerful, the algorithms and the tools got so powerful, it became clear that these were kind of the next natural evolution step in what we had already been doing in fluids.
Mm.
At one point, you mentioned deep learning, and they asked, what's the difference between machine learning and deep learning?
Yeah, that's a great question. It's funny, the farther we go, so I got into machine learning about 10 years ago. And at that point, deep learning was really not even on the list, on the top 10 list of machine learning algorithms. Like in 2010, there was this paper, top 10 algorithms in machine learning, and deep learning was nowhere to be found. It was things like support vector machines and decision trees and AdaBoost and, like more classic, it's funny to call them classic methods. And so again, you can build models from data with optimization and regression that are not neural networks, that are other models, other forms of models. Since about 2012, especially with ImageNet and subsequent successes, deep learning has gotten so powerful. The algorithms to train these networks are so powerful. The data sets are so large. The GPUs that we train them on have gotten so much faster and bigger that really neural networks have kind of eclipsed all other algorithms for really big, really hard problems like image recognition or image captioning and things like that. And so, in a lot of places, machine learning is starting to become synonymous with deep learning, but that's just because deep learning are the techniques that work the best on the hardest problems, not because they're the only solutions. And so I actually expect that in the next 10 years, we're actually going to find a resurgence of these classical machine learning models that often will work better for extrapolation or for incorporating physics or for other things. And so, yeah, like it's almost a little bit of a pet peeve of mine. Like we love deep learning, it's super powerful. It's undeniably the future in many fields, but it does have these kind of big weaknesses of interpretability and generalizability, especially for limited data sets, and especially when the training data set is not indicative of what you want to use your model for in the future. And so I like to point out that there are, this huge kind of wealth of other data-driven optimization techniques out there.
I was also curious on is the Cindy algorithm the only algorithm that you guys have, or is there are there any alternatives or?
Yeah, I mean, this is just one of 30. I mean, we do a ton of different algorithms for sparse sensor placement, for control, for modeling, for prediction. Cindy is probably the most popular or kind of widely used of the algorithms we've developed. It satisfies a real need. I think that's why I talk about it usually, and that's why it's been kind of why people are drawn to this method, is because people fundamentally like simple models that are explainable and interpretable, and you can train with limited data and things like that. But I mean, there's tons and tons of different algorithms and models that we use depending on, just like all of machine learning is not neural networks. Like, we have all of these different flavors of modeling for dynamical systems depending on how much data we have or how big the problem is, or what our ultimate goals are. Yes, this is just one approach. Great questions.
And following up with the Cindy algorithm, what else could the Cindy algorithm be used for in the future other than fluid dynamics?
Yeah, so I'm only showing examples of fluids here, but it's already been applied to a huge variety of problems in other sciences. So people have used this to model the spread of diseases, to model neuroscience systems, vibrational analysis for structural modeling for earthquakes and building safety. People have used this to model laser systems and fiber optic systems, fusions. Yeah, kind of population dynamics. The sky's the limit. If you have a system that evolves in time and has patterns, you can apply this technique, which again is another one of the reasons why we talk about this one and not necessarily all of the other ones, is like, this seems very widely applicable. If you have data that evolves in time and has patterns, you can kind of apply this technique.
So like related to your research on like fluid dynamics and like machine learning, is there like anything specific that you're like researching on, if you don't mind me asking?
Yeah, absolutely. So we have a lot of research in this area, and it's pretty diverse. So it ranges from fairly industrial applications, things we would work on, you know, with companies like Boeing or Amazon, you know, Air, things like that, to pretty theoretical dynamical systems questions. How much information can I extract from a partial measurement of a system? The partial measurements is one of the most exciting areas. So imagine you have a complicated system, but you don't see the full movie. You only see a few point measurements of that system. You just see time series of a few measurements. This is what we have in brains. We're kind of like, brain measurement technology is like 100 years ago fluid dynamics measurement technology, where we know the system is super complicated. We'd love to have a 3-dimensional movie of every neuron in your brain. But right now, you know, best we have in a lot of cases is a little tiny grid patch of maybe 100 measurements and little time series of those measurements. So how do you infer from limited measurements that are incomplete, that don't have the full range of what you want to be capturing? And so that's a really important active area. And you can think of a million cases where that would be useful. So I've got a wing and I've got one measurement on that wing. How do I take that one measurement and infer what the other fluid states are doing? Or, you know, I got 2 measurements in the brain. So people that have these bad seizures, like uncontrollable seizures, oftentimes one of the last resorts will be to implant a medical device that actually measures, you know, nerves in your brain, and then can stimulate certain nerves with like rhythmic activity to try to de-entrain that seizure. And they have very limited measurements. They're not talking about even 100 measurements. They might have 1 or 2 voltage signals in time. And from that, they're trying to infer this extremely complex spatial temporal partial differential equation of wave propagation in the brain. So, you know, really interesting applications. But I think that's one of the big areas where, you know, how do we make this work with way less data than what we would normally have to train like a deep learning model? Yeah.
Yeah, a question similar or relating to your research. If you don't mind sharing, what are some challenges you faced in your research, or what is the biggest challenge you've faced so far in your research?
Yeah, I mean, I'm an optimist. I think of challenges as opportunities. And so I think, you know, generally speaking, that's been a helpful perspective, is that, you know, like I actually look for challenges. I want challenges because challenges are where the biggest opportunities are. So I don't know. What are some of the challenges in the research? I really love what I do. I feel like it's super satisfying and fun. Like I get to work with bright young people who are in a phase where they are developing their careers and their skills. That's what they want to do. And so we're kind of invested in a common goal. It's difficult because my students, like there's a training process for PhD students where they train for about 4 or 5 years. And so they start out having good basic skills from undergrad, but not, you know, amazing research skills yet. And we build up until they're excellent researchers, and then they go leave and start their own labs or go leave and get a job. So, which is great. It's amazing when your students go do great things, but it is, you know, an academic lab, you're always training people until they're, you know, just amazing, and then they leave. So that's definitely a challenge, but it's also like probably the best thing about the job is getting to be a part of that process.
Oh, that's really nice. And for the final question for the audience, do you have any advice for like middle or high school students like trying to get into the field of AI?
Yeah, absolutely. So in your lifetime, in your professional lifetime especially, these techniques are going to become tools that everybody has basic proficiency with. So, you know, 40 years ago, computer science was a separate science. There were scientists and engineers, and then there were computer scientists and computer engineers. But now, like, you know, we are all interacting over our computers, and you all know how to use a computer, and I know how to use a computer, even though we're not computer scientists necessarily, right? And so even if I am just a fluids engineer, I am expected to have basic proficiency working with the tools of computing. And similarly, in the next 10 years, I believe that that same transition is going to happen with machine learning and artificial intelligence, where this is not going to be a separate field of science. This is going to be a tool that all scientists and engineers have basic proficiency with. There will still be focused, you know, researchers that research that topic, but they will be making those tools available so that we all use them, just like we use our laptops and desktops. If you want to distinguish yourself, if you want to be on that cutting edge of development of this exciting field, I would say really be sure not to skimp on the fundamentals. Math is the basis of all of machine learning. This is all linear algebra. It is all statistics and probability. Like, you need a foundation in mathematics. You can definitely get 70% of the way there with very little math, but to get that next step to really be at the frontier of your field, you need to have that solid math foundation. Similarly, you know, don't just do theoretical machine learning and theoretical learning in general. Like, pick a programming language and get your hands dirty. Like, pick some projects, get things working, try things out. You know, Python is a great language to kind of get up to speed quickly and start working on things. So, I mean, those would be my real recommendations. This is going to be a tool that everybody has soon. Math will always be the thing that is kind of helps you really develop advanced technologies.
Yeah, that's some really great advice. Thank you.
Thank you.
Unfortunately, that's all the time we have left today. I'd like to end off by thanking Dr. Brunton for taking the time to present a keynote speech for us today.
And thank you guys all for attending today's session with PTC Seattle. And we hope you had a great experience as we did. And our next session will be on July 2nd from 5:30 p.m. to 6:30 p.m. Eastern time, where we will have the interactive intelligence team from the University of Washington leading a workshop. And this workshop will be about understanding neuroscience and AI for the development of human-like intelligence.
If you have any questions, feel free to reach out to us on Instagram at PTC Seattle. Once again, thank you for taking the time to participate in PTC Seattle's track of artificial intelligence.
Thank you all.
Thank you.